Up, give me 1 sec. I know you guys are just on time. Well, technically a little bit late, but I had an interesting day and got pulled into some extra meetings, and so I was a little bit late. So we'll get started in just a sec. Settle in. It'll be fine. Okay, cool. Well, we're ready to go. Let's just get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. Pray that you would continue to help us accomplish all the things that we set out to do, that you would get us through the rest of this semester and help us get some rest. In your name we pray. Amen. All right. All right. So today is the day, right? The last official lecture. If we get done early today, you guys can use the remainder of class to work on your projects. Right? Talk about that. I didn't have a chance yet. They didn't tell me they were done. But you know what? I'm gonna go check the prep room real quick because maybe we might have some parts for everyone. Let's see. Nope, nothing yet. So check with me. We'll probably have something by Friday, I would guess, because most everybody, you guys all got them in Monday and Tuesday, so we should be good. Depending on right what else needs to be printed and where we are in the queue. If I don't hear anything by the end of the day, I will send an email to the lab staff and ask about what they think is. Ask them when they think it'll be done. All right. So I know this has the same title as the last lecture, but it's not. It's not. All right. So one thing before we get into this, last lecture that was totally messed up, so it's not going to be posted. Okay, on YouTube. The video completely messed up. There is audio. I can post the audio if you guys want. But there's the video is all, it's stuck on the first title screen. So you will literally see this for like 2 hours. So I apologize for that. This time we should be good. Looks like this time we're good. I'll keep checking it throughout just to make sure, but it looks like this time, looks like we're good. Yeah, looks like we're good now. In terms of this, right, I'll pause that real quick. Let's pull this up. Don't understand the Quizzard. He's a mysterious figure. It's not meant for you to understand the Quizzard, right? Or why he or she torments you. So, but yeah, all right. So it looks like we're doing pretty good. So what did we do last time, right? Well, here's the assignments, right? We've got a homework due tomorrow night. Make sure you do the last homework. We're gonna focus on three-dimensional problems and gyroscopic motion, which we'll get into more today. We've got exam 3 on Friday, and then your CLC stuff, right? We will see what we can do for Monday, right? If we can't get in on Monday, I've got a backup plan, so don't worry about that. We might be able to do something in class on Wednesday next week, where you guys finish your builds and then we test using an air compressor. The only difference is then you guys have to look up the equation for figuring out how much airspeed you have coming out of the nozzle, right? which should be plug and chug because you'll know what the pressure is and you'll know what the diameter of the nozzle is, and those are the two things that are important for that, really. Okay, so there's this stuff, right? And then the very last day, we'll have our presentation, and you guys will turn in your papers, right? And everything will be great. All right, so today we're going to talk about motion of a rigid body in 3 dimensions, we've already been talking about it. Then we're going to talk about motion about a fixed point, right? So 3-dimensional motion around a point that's fixed in space. We'll talk about motion of a gyroscope. It says exam 3 review. I can answer any questions that you guys have on about exam 3. But if we have any extra time, right, you guys can get together in your groups and talk about. I was hoping we'd have some parts right now. But who knows? They might get delivered during class. So if they do, we'll have them. If not, we'll just play it later, right? So let's start with this by means of recap, right? 2 L-shaped arms, each weighing 4 pounds, are welded at a third point. At the third points, sorry, not at a third point, at the third points, right? So each one is a third of the way along this rod, right? Of the 2-foot shaft AB, right? So I've got this shaft AB, right? I'm going to route these 2 L-shaped bars onto it, right? Why? Saturday and I'm bored, right? We got this welder, why not? Okay, so knowing that the shaft AB rotates at a constant rate of omega, 240 RPM, we need to determine the angular momentum of the body about B and its kinetic energy. So right off the bat, we know we're going to be using angular momentum and energy, right? Probably conservation of energy. This is a weird system though, right? Because these L-shaped bars, as it rotates, right, this is going to do some weird stuff, right? So how do we handle this? Notice we've got our coordinate system set up and the end on B there, right? We've got this set up. Y, X.
Are you going to run to tell how far away they are from the axis?
Yeah, so we're told that they are at the third points of the shaft, right? So if you divide this into thirds, this should be 1 foot from this end, and this should be 1 foot from this end, right? Well, all right, no, it's a 2-foot shaft. That would make sense. That would be a 3-foot shaft. So it's going to be 2/3 of a foot from each side, right? 2/3 of a foot. That makes sense, right? 2/3 plus 2/3 plus 2/3 should be 2. Okay. Let's try that again. 2/3 of a foot. 2/3 of a foot. Ooh. Okay. So what do we do here, right? So what's the general strategy? The general strategy here, so the part rotates about the axis AB, right? Everything is rotating about this central axis. So first we need the mass moment of inertia matrix, right? So we need our IXX, IXY, YY, IZZ, right? We need all those. So that's the first thing we're going to need to do. Then we can compute the angular momentum of the the rod, using the moments of inertia. Right, so we're going to find the moment of inertia. Right, this is not an easy read off a table, right? This is going to be a complex geometry, so we're going to have to use, an L-shaped rod and an L-shaped rod and a regular rod to determine our moments of inertia. Right, and we're going to compute the kinetic energy, right? So there's 3 parts to this. Find the matrix of your moments of inertia, compute the angular momentum, and compute the kinetic energy from the angular velocity. Okay. So here's my thing again, right? So what are my knowns? What do I know? I know that the whole thing weighs 4 pounds. That means the mass has to be 4 divided by 32.2, which is 0.12422 pound-seconds squared per foot. That length A, lowercase a, is 8 inches, which is 0.667 feet. Omega z is equal to omega, which is 240 RPM, which I convert to radians per second. And how do we do that? Let's multiply by 2 pi by 60, right, to get rid of the minutes. So we get 8 pi radians per second. We have no rotation in the x direction, right? There's no rotation into the board, and there's no rotation vertically around the vertical axis, right? This just rotates around z. So we need to find HB and T, right? And remember, T is our kinetic energy, and H sub B is the moment, or not the moment of inertia, I'm sorry, the angular momentum about point B. Right, so there's only rotation about the z-axis, so what relationships are helpful for us? And so what relationships are helpful for us? So these, we're going to use HB in the x, we need IXZ, right? So we need all of these, we need the x sub xz, yz, and iz, right? We need iz, iyz, and ix, right? Remember that long equation that we put up on the screen. Remember that long equation we put up on the screen last class, where we had all of the different components. We had ix times omega x plus ixy times omega y minus ixz times, right? We're just stripping out all of the different, where we had 3 moment of inertia. I don't know why I keep saying 3 angular momentum equations. Where we had 3 angular momentum equations that all had a bunch of terms in it, right? And all we've done is stripped out the omega x and the omega y terms from these 3 equations, right? So we can split the part into 4 different segments and determine IXZ, IYZ, and IZ. So what's the mass of each of my segments, right? Because I know the total thing is 4 parts. So we're going to split it into 4 segments, right, that have 0.06211 pounds seconds squared per foot of mass. So we've got to fill in this table, and we're not going to, right, so how do you fill in this table? You got to go into the charts and figure out where, so what are our 4 segments here, right? What are the 4 segments we're looking at? You got this segment, this segment, this segment, and this segment. Okay, so how do we find IXZ and IYZ from these? You go into the table and you look at what it is for a bar. You know that the length is, right? And we can figure it out from there. So it's M prime, right? It's the mass times negative A times A, and the mass times 0.5 A times A. And this, you can't really see it here because of editing reasons. So that's IXZ and this is IYZ. And again, this comes from the table. You go in for a rod, right? You go in for a rod and you see what it is, and you just go with it, right? We do the same thing for part 2, same thing for part 3, and for part 4. Again, these equations come from a table or a chart, which you will have if you need them, right? And then we add them all together, right? Because hopefully this is jogging our memories from statics when we first heard about moments of inertia, right? Where you fill in the table And you have all of your composite pieces, and then if you want the total moment of inertia for something that's made of composite pieces, we add all of them together. Right? If we do that, right, we get 1.5 m prime a squared as both. So what's that, Zach?
What's
A is the length, 8 inches. Right?
I know it's important, so different.
Yeah. So if you're looking at the tables, they have pictures of the geometries and they'll identify what the different lengths are that you need. Okay. And so what we got? We got 1.5 m prime a squared. We know m prime, right? We just figured that out. We know a is 8 inches. So we can figure this out, right? So how do we find IZ? We're going to use the parallel axis theorem. Right? We're going to use the parallel axis theorem. We're going to do parts 1 and 4 first. And remember, what is the parallel axis theorem? The parallel axis theorem is this, right? It is the moment of inertia, I sub z, plus the mass times the change in, times the mass times 1/2 a squared plus a squared. Right. So it is, what is it? It is the moment of inertia plus the mass times the distance that you are squared. Right? The distance that you are away from the point B squared. That's what it is. Does that make sense? Remember, each one of these lengths here, right, was also 8 inches, right? Because 2/3 of a foot should be 8 inches. Yeah. So this is 8 inches. This is 8 inches. Right, and so if you're looking at how far from B point this part 1 is, right, that's going to be m prime plus d squared, but that d is 1/2 a squared plus a squared. Okay. Parts 2 and 3 are also equal to one another, right? So the horizontal parts are also equal to one another, and that's just 1/3 m prime a squared. So where does that come from? That's digging deep, way back to statics, like the very last part of statics, right? This should have been something that you guys covered with Dr. Kong. Digging deep, doing mass moments of inertia for composite geometries, right? Once we have this, right, when we've seen that once we have this, this is important for us calculating our angular momentum h, right? So h in the x direction about point B, right? H at around point B in the x direction is what? Well, that's going to be negative I xz omega, right? We know I xz, we know omega. We can plug all that in, and we get the angular momentum in the x direction. We do the same thing in the y direction, right? We know the equation for the angular momentum in the y direction about point B. Look, in the x and y direction, it's the same. And about hz is 2.3126, right? So once we figure it, the hard part here is figuring out I, right? The hard part here is figuring out what is I in relationship to point B. That's the hard part. So my total vector, right, is just the x component in the I direction plus the j component, or the y component in the j direction, plus the z component in the direction, right? And that's the first thing they asked us for, right? Was the angular momentum about point. And I know that we didn't go over how to calculate IXX and IYY, IZZ, all the different I's, right? But most of the time, most things, even if you do composite ones, right, can be added back together. You can at the very least find it about the center of gravity, right? Because for this thing, where would we expect the center of gravity for this to be? Right? Well, if it was just the bar, it'd be in the center. These two are evenly spaced though, right? And opposite, so it's still going to be right about in the center, right? Yeah. Probably lift it up off the bar a little bit because there is some mass on the upper half here. So in the z direction, you'd stay the same, but we will lift off the bar somewhat. Right, based off of the handles being there. What about kinetic energy? This should be a little bit simpler, right? Because the kinetic energy is what? Well, it's 1/2 I omega squared plus 1/2 mv squared, right? We have to do it in all the directions, and this isn't going to be translating, right? So we shouldn't worry about it. This is a pure rotation, right? This is a pure rotation. So we have to take the x component, the y component, and the z component, and we have to take the off-axis components as well, right? We calculated all of those already. We know Ix, Iy, Iz. We know Ixy, Ixz, and Iyz. Right? This is now plug and chug after you get I. And we're left with this. Another thing to remember, right? Those are 0. Those are 0. Those are 0. That's 0. And that's 0. Right? Remember, we only have angular momentum or angular velocity in the z direction, right? All the other ones were 0. So anywhere that a wx or omega x or omega y shows up, that goes away, right? And so all we're left with, like it shows us here, is this, that one term. 1/2 Iz omega squared. Right, we calculated I sub z earlier. There it is. Plug in, chug. So again, in my opinion, the difficult part of these problems is not applying the kinetic energy formula, right? The difficult part here is calculating I correctly, if you have to do it. Now, we've done a couple problems where we don't have to calculate I, right? Where we just use whatever is on the table, and that's fine too. But understanding how to come up with I, right? And remember, if you have a composite geometry, you break it into the pieces that you know. Always break it into the pieces that you know. Right? Like in this case, I've got a rod of length 8, right? In each of these cases. Right. No, you guys have any questions on this problem? Right. The equation sheet for this will include three-dimensional the three-dimensional variants of the equations, right, for H and T. Well, probably not T, but for H. H is not intuitive. Well, no, I take that back. For both, it'll have both. Okay. No questions? So what about motion of a rigid body in 3 dimensions, right? And we've been talking about this. So angular momentum and its rate of change are taken with respect to the centroidal axes, right? So we measure the centroid, right? And the centroid has some x, y, and z prime fixed orientation. And the transformation of omega into h sub g is independent of the system's coordinate axis. Okay, so what does that mean? Well, it just means that it's convenient for us to use a body fixed axis g of x, y, z, where the moments and products of inertia are not time dependent, right? So So as this moves in 3 dimensions, right? As this moves in 3 dimensions, if we have a rotating frame of reference, right? Then we have to remember what happens when we have a rotating frame of reference, right? We have to do all these weird, not weird, but we have to do all these Coriolis effect things, right? We have to measure, what is the relative position and in time of this object, right? If we use a fixed axis, then we don't have to worry about the time dependence of this, right? I don't have to worry about how it's rotating and what angles it's rotating through. So we can define the rate of change of h sub g, right, as the angular momentum about the center of gravity with respect to the rotating frame. And if we use this rotating frame, right, well, this is all the stuff that we talked about earlier, right, for 2 dimensions, but we're adding another dimension. We're adding a 3rd dimension, right? So omega is equal to omega, and g of xyz is chosen to correspond with the principal axes of inertia, right? And hey, look at this. These are what are known as the Euler or the Euler, however you want to say that, equations, right? So the sum of the moments in the x about the x-axis equal to I bar x omega x minus I bar y minus I bar z omega y omega z. Right? So these are a bit more manageable than the angular momentum equations, right? At least I think so, because we don't have to worry about the off-axis. We don't have to worry about ixy, ixz, right? We don't have to worry about that. You just have straight ix, iy, iz. So what is this telling us, right? It's saying that the system of external forces and the effective forces are equivalent for general 3-dimensional motion. Since the system of external forces are equivalent to the vector couple MA and HG, right? So some of my moments has to be equal to the change in my momentum, right? Some of my moments is the change in my angular momentum and vice versa. What about rotation about a fixed point, right? Because lots of things rotate about a fixed point. So for rigid body that rotates around the point O, right, we've got this. And again, we're using this rotating frame. And for rigid body rotation about a fixed axis, we can write this. And that's to be expected. We just did this in the previous problem, right? In the introductory problem. Why? Well, if it's rotating about a fixed axis, then it's only rotating about one of them, and the other 2 are set to 0, and so we're left with this equation, right? These sets of equations. But what if we want this about some fixed axis, right? Point O. Well, that's also the sum of the moments about point O equal to h dot O plus omega cross h sub O, which gives us this nasty looking beast of an equation down here. Right? Notice that this is dependent on the angular velocity, right? And the angular acceleration, right? Angular acceleration, angular velocity. Right, so there's 2 components that we need to remember for this equation. It's right here. Negative ixc minus iyzj plus izk times alpha plus negative ixcj plus iyzi omega squared. This leaves us with x, y, and z components that look like this, which is admittedly a lot nicer looking than writing it in the vector form. right? So the sum of my moment, right? So for an object rotating about a fixed point, we have this, where the sum of my moments in the x direction is equal to negative ixz alpha plus iyz omega squared. And the sum of the moments about the y-axis is equal to negative iyz alpha plus ixz omega squared, and the sum of the moments in the z direction is iz alpha. So unlike rotating in a planar motion, right? Unlike a two-dimensional problem where we're constrained to rotate in plane, right? Normally, when we were doing this before, we were only talking about rotating in the XY plane, right? We're rotating about the z-axis. And in this case, because we're rotating in other directions, it's not just a function of the moment of inertia times alpha. You have to add your off-axis components back. Right, so these are the equations we just had up on the previous screen. They haven't changed. The rigid body rotation around a fixed axis, this is what we get. This is what we get. If we have something that's symmetric with respect to the xy plane, then we're just left with iz alpha, right? And if it's symmetric with respect to the xy plane, what have we created? We've created motion, a general plane motion situation, right? We've created a two-dimensional problem with a single axis of rotation. If it's not symmetrical, the sum of the external moments will not be zero, even if alpha is equal to zero. And so if it's not symmetrical, there's no way that we're not balancing these moments, right? Now think about why that might be, right? Because what is a moment? A moment is a force times the distance away that it is applied, right? Perpendicularly speaking in two dimensions, right? It's r cross f, right? Moment is r cross f. The cross product of the distance, my distance vector in f, right? So we're gonna do this. We're gonna try this, see if this works. Too bad it took me until the last day to figure out what this might be. Okay. So if a moment is r cross f, right? And say we have something that is symmetric, right, in space. Okay? And I'm going to measure it from, here's my coordinates, right? Something like that. Okay? This distance to G, right, is R. No matter where I put a force, if I have a force here and here, right? If I break this into X, Y, and Z components, wherever that is, right? Let's just say I'm applying a force here in 3 dimensions. So I've got this X, this Y, and I've got an X, Y, Z force right there. That distance R is symmetric in all directions, right? This R, because it's the radius of a circle, because it's symmetric, we're going to get two portions that cancel each other, right? We'll get two things that cancel. If it's not symmetric, right? Think about it in a two-dimensional setup. And something that's not symmetric, right? If I apply a force here, and we're rotating about there, the total distance to this point is not symmetric in two of my planes, right? And so I can't just cancel. I will have an x component and a y component that do not cancel. Right? So not being symmetric is not problematic, right? That's not the word I want to use. It's not that it's problematic, but not being symmetric makes it so that we can't just cancel things, right? Because the x direction component and the y direction component are not going to cancel when we are not symmetric. We still have some angular velocity that plays a role. All right, so if you had a shaft that looked like this, right, a rotating shaft requires both static, the omega equals 0, and dynamic, omega not equal 0, balancing to avoid excessive vibration and bearing reactions. So you need the statics and the dynamics here, right? We need to be able to discuss the static loading. We also have to discuss the dynamic loading, right, when this is accelerating, so that we can determine whether or not we have excessive vibration caused by this being not a straight line, right? Because remember, the weight of this, well, I guess this is vertical, right? The weight here is pulling it down, but this side is producing a moment about the center. And this side is also producing a moment about the center, right? So it wants to shake as it rotates. Let me ask you guys. The device to the right rotates about the x-axis with a non-constant angular velocity, right? So non-constant means that it's changing, right? So when you have a non-constant angular velocity, what does that mean? What is that key in your brain? What happens if your velocity changes with time? What is that called? It's called something very specific. If your velocity is changing as a function of time, right? What is your system doing? It's accelerating, right? So this is telling us that we have some acceleration, right? So if we go back, this is telling us that we're in the dynamic case, right? Now, why is that important? Well, which one of these is true, right? You can use Euler equations for the provided x, y, z axes. Or B, the only non-zero moment will be about the x-axis. C, at the instant shown, there will be non-zero y-axis bearing force. Or D, the mass moment of inertia Ixx is 0. Now we probably, this is 25% chance, right? So, all right, what are the Euler equations, right? Let's go back and look at them. There they are. Right. So according to this, right, I'll go back and read what it said. You can use Euler's equation to provide for the provided x, y, and z axes, right, to find the moment. Can we? Can we? Well, this is going to be, right, isn't the y direction going to be 0? The z direction is going to be 0, right, because we only have omega x. So the only one we're left with is the sum of the moment and the x. So, I mean, I guess we could, right, but not super helpful. The only non-zero moment will be about the x-axis. I think we've just proven that it's not, right? Well, I think actually we did just prove using Euler's equations that it is, right? The only non-zero moment will be around the x-axis, right? Because Why? Well, this is rotating through a fixed point, right? So let's go back to this equation here. Right, where is it? Let's go back to this one in the red box, right? All right, we're rotating about a fixed axis with the specified omega. So x, y, right? These are all, it's not, right? All of these are going to be, we can't use Euler's equations. The whole box here gives us moments in the x, y, and z direction, right? Because there is an alpha. Alpha is non-zero, right? Because our omega is changing with time. At the instance shown, there will be a non-zero y-axis bearing force, or d, the mass moment of inertia, ix-x is 0. Well, it is d, right? Why is it not c? Because at the instance shown, the bearing force in the y-axis has to counteract not only the weight of the object, but the fact that it is accelerating at this point, right? And so it wants to pull everything down. The bearing's got to hold it up, right? It turns out that Ixx is 0. Why is Ixx 0? Because our center of gravity sits on the x-axis, right? So center of gravity sits on the x-axis. We are actually symmetric about the x-axis here, right? We're symmetric about the x-axis. Okay, let's talk about this propeller. It's another problem that we can walk through, right? So we've got a four-bladed airplane propeller. It has a mass of 160 kilograms and a radius of gyration of 800 millimeters. If I know that the propeller rotates at 1600 RPM as the airplane is traveling in a circular path with a 600-meter radius at 540 kilometers per hour, I want to determine the magnitude of the couple exerted by the propeller on the shaft due to the rotation of the airplane. So when we hear the word couple, we want to know about moments, right? So we're going to have to use these moment equations, right? A force couple, right? Remember, in case we forgot, right? In case we forgot, draw it on the board again. In case we forgot, right? Here's a generic bar, and I'm going to apply forces that are both some distance d, the same distance d away from the center of rotation, right? That's what I've got. So I can replace both of these forces, right? This is equivalent to a system in which I have a single moment that turns this, right? And you can't see that color whatsoever. But there's a moment. You can kind of see it. Not really. Let's try that again. Is that any better? There we go. You can see that. Right? So this system in red with two forces, one pushing up on the left and down on the right, is going to cause a rotation, which we can describe with this moment, right? So there's some moment that will can be equivalent and take the place of this force, right? That's what we're talking about with a force when we say couple, right? When we say a couple, that's what we're talking about. So we need to find the magnitude of the couple. We need to find the magnitude of this moment that's being applied here, right? Right, so that's just a repeat. So what is it that we're doing? Right, so we need to determine the overall angular velocity of the propeller. That's number one. Why do we need that? Well, remember, all of our momentum equations, all of them, right? Because this is rotation about a fixed point. All of our moment equations have omega and alpha in them. So we need to figure out omega. Now, what are we told right off the bat? This rotates at 1600 RPM. Right? The propeller itself rotates at 1600 RPM. So what should that tell us about alpha? What should that tell us about alpha? Right? Then we need the mass moment of inertia for the propeller. So we're going to have to find it for all the blades and add them together. And finally, we calculate the angular momentum of the CG. Oh, sorry, not finally. So then we calculate the angular momentum about the CG of the propeller. And then finally, calculate the time rate of change of the angular momentum to get my moments. Because remember, my moment is just a time derivative of my angular momentum. Okay. It's really quiet in here without the air conditioning on, let's say.
The mass moment of inertia, what we usually call I.
Yeah, that's I. I is the mass moment of inertia. So, right, calculate the moment that must be applied. Okay, so this is the general things that we're going to do. Right? We're going to determine the overall angular velocity. Right? Why? Because we know that in order to get to find anything else that we've been talking about, we need omega. Right? To find anything else, we need omega. All right. Everybody tracking so far? We good. Any questions? No, we're all right. Yeah. First things first, is establish the axes of rotation for our propeller. So here's our propeller, and we're going to say that for the propeller, we've got Z, right? So I'm using this rotation here, right? I'm using these axes, right? Here's Z, Z to the right, X coming out of the board. I'm sorry, can't read my own writing. X coming over here, right? Y up, and Z positive out of the board, right? So X, Y, Z. X, Y, Z. Right, and so remember what's going on here with the propeller. We know a couple of things. We know that the aircraft is in a circular pattern, right? It's flying. So the propeller itself is actually going to be moving forward, right? There's some velocity associated with it, but there's also has angular velocity, right? Because it spins, but as it spins, it moves forward, right? So you would get this sort of pattern in space, right? If you were to track one point on the propeller, it would move forward and just make this circle, right? Look kind of like a spiral. Okay, so we need the x component of the angular velocity, right? We want omega x. We know omega x, right? Because we were told omega x. Right? We were told omega x. It was 1600 RPM, which we can convert to rad per second. We're going to get 167.55 rad per second. So now we need the y component. Now remember, and I'll draw this one on the screen here. If we're looking at the path that this airplane takes, it's this, right? That's not really a circle. Let's try that again. I can do a circle, maybe. Hey, that's circular-ish. Nailed it. All right, I'm gonna go home now. You guys have been great. Okay. So this is moving in a circle, right? And we've got this airplane moving around in a circle. So if we're measuring everything from the center of this trajectory, right, this propeller has some omega y, right? Because remember, it all depends on where we're measuring this from. So there's some rotation about the y-axis that we need to deal with, right? So how do we find that? And on our diagram, it says that that's capital omega. And normally when we use capital omega, that means that's the rotation of my frame, right? Well, we can figure this out from the tangential velocity, right, v, which we were told was 540 kilometers per hour, right? Because that's how fast the airplane is going. And so at any point on this circle, it has to have that velocity. And we know r, right? Or rho. Right? Did we know rho? Let's go back and look. Right. So that's the radius of curvature, right? And if we dig way deep, and we remember back to when we talked about, well, remember, so this is two-dimensional, right? So omega is equal to v divided by r, right? Which is what we got. The only thing is we had to convert 540 kilometers per hour into meters per second. That is it, right? But remember, velocity, tangential velocity is always omega cross r. But in 2D, that's omega times r. And so if we rearrange it, we get omega is equal to v divided by r. That's where we get this. There should be no rotation about the z-axis. Right? There should be no rotation about the z-axis. Should be no forward and backward tilting. So omega z should be 0, right? Omega z should be 0. Again, how are we supposed to know this from the way this is set up, right? Because remember, it's all dependent on, it all depends on where you are measuring from, right? As with a lot of the things in dynamics, right? It matters about what's happening to your frame, right? If you're standing at the center of this curving path, right? You're standing at the center of the trajectory that the airplane is taking, and you're watching the propeller, it's going to look to you like the propeller is not only rotating about its x-axis, but also that it's trying to twist, right? That's what it's going to look like to you if you stood at the center of this and you were watching this plane. It would look like, as this moves around you, right, the propeller itself is twisting around the y-axis. I'm going to have to erase that. So then we can find the mass moment of inertia in the x direction, right? We were given radius of curvature, yes? Let's go back and take a look. Radius of gyration, right? Yeah. This is another big thing. We were given radius of gyration. Whenever we see radius of gyration, we should get really, really happy, right? Because when you know radius of gyration, you can immediately pick off I sub x. Why just I sub x in this case? Because we're rotating about the x-axis, right? I sub x is m k bar squared. So there's I sub x. Oh, sorry. There's I sub x. So if you're given the radius of gyration, remember it's just mk squared to get I. How are we supposed to know that this is Ix and not Iy or Iz? Because this is spinning about the x-axis, right? Spinning about the x-axis. I think we did another problem a couple weeks ago where we were given multiple radii of gyration, right? Typically, you're being given radii of gyration when you are spinning about a fixed axis, typically. So can we find angular momentum about the center of gravity here now? Well, here's the equation, right? YZ is 0. Remember, there's a bunch of other terms here, right? Omega Z is 0. And remember, there's a bunch of other terms here that are dependent on omega Z, right? So if we wrote out the full equation here, we would have Ix omega Xi plus Iy omega Yj plus Iz omega Zk plus Ixy omega Y omega X, right? Plus all those off-axis terms. But they all go away. This is what we're left with. So we have to take the derivative of this, okay? So we take the derivative of it because we want the time rate of change here. And if we take the derivative of this, we also know that the derivative is equal to this big equation here, right? H dot G, G, X, Y, Z plus omega cross H sub G, right? Well, we can break it down, right? We get these equations here. We get omega cross H sub G, right? Omega cross H sub G is just omega Yj cross Ix omega Xi plus Iy omega Yj. H dot G of X is 0. Why is it 0? Because omega X and omega Y are both constant. If you take the time derivative of that top equation, we know that we have constant angular velocities, right? And constant angular velocity means we're not accelerating, which means if you take the derivative of a constant, you get 0, which is why H dot G is 0 here in 4G XYZ. So we're left with this, right? We're left with this, and if we take that cross product, the only thing that we're going to be left with is negative Ix omega X omega Y K. That's what we're left with. Now we know I sub X, we know our omegas, so we can plug it and plug it, and we can find the time rate of change of our angular momentum about point G. Okay. Is that okay? Everybody, any questions about that? Remember, let's do this. All right, there's omega Yj cross Ix omega X Iy omega Y, right? That's what we have. Well, I guess I gotta stop the sharing on this. Let's do that. So this is what we have, right? So if I take this cross product, right? I cover I, I'm left with 0, 0, 0 minus 0 in I direction. All right, cover J, cover the central one, I've got 0 times 0 minus Ix omega X times 0. All right, that's the I cross K, remember our circle, right? I cross K is negative J, so this is going to be negative 0 minus 0 in the J. And then finally, if I cover up X here, I've got 0 minus Ix omega x omega y. There it is, and that's the same thing that we came up with on our slide, right? Just did the cross product. So it turns out for us, we didn't calculate IY, but we also don't need IY. We can plug in for these things, solve it, and we know what the rate of change of our momentum is. So now we need to figure out the moment that needs to be applied to the propeller shaft, right? How much, another way of phrasing this, another way of thinking about this is we're trying to determine how much torque you need to apply to get this omega out, right? To get out these speeds, right? To get this motion out, how much torque do I need to apply to this propeller from the shaft, right? That's another way of thinking about this. So how do we do it? Well, remember, the moment is just h dot g, right? So you already found it. So what about the force couple, right? So we need, what we want to do, right, what we're asked to do is find the couple that is exerted on the shaft by the propeller, right? So in reverse, what do we have, right? So the propeller and the shaft are connected, right? So essentially we're looking for the reaction forces here, right? Well, it's just going to be the opposite direction, right? Because they are connected, because we were talking about the internal forces here, they have to be equal and opposite. So if there is a moment of negative 4.29 kilonewton meter in the k direction applied from the applied to the propeller shaft, then the propeller, then the shaft, then the propeller has to exert an equal yet opposite moment on the shaft, right? So the shaft produces, we're giving this much torque to the propeller shaft. So the propeller has to be counteracting that, right? It's a reaction. Does that make sense? If these two things are rigidly connected, right? You twist this, right? If I'm twisting this marker and I was to cut it, and I'd magically be able to cut it, you would see that both sides, interiorly, depending on which side you looked on, one would have a moment going one way, and the other would be pointed equal and opposite, right? If I was going to pull a string, right? Think about it this way. You're playing tug of war, right? And you're evenly matched and nobody's moving anywhere. And then I cut the rope, right? Both teams are going to go in this direction, right? Which means that the rope had a force that was pulling equal and opposite to keep itself together. Okay, same principle here. Is there any questions on this? Turns out, right, if we can get here, we've got everything that we need. It's just being phrased differently, right, to how we think about it. So the amount of angular momentum, the time rate of change of my angular momentum is my moment, right? And we can have reaction moments as well as applied moments. Okay. So the airplane propeller has a constant velocity of positive omega in the x direction, in the x dot direction, right? X, just call it x direction. The plane begins to pitch up at a constant angular velocity. True or false, the propeller has zero angular acceleration. So you're going this way, you have a constant x rotation, constant angular velocity in the x direction. And your airplane starts to pitch upward, right? It starts to tilt up. Does the propeller have zero angular acceleration? True or false? That was weird. Hope everyone's okay. What do you guys think? Right, so here's my airplane. It's totally an airplane. It's not a marker. It's an airplane. And the propeller is turning in the normal direction. This is going forward. Then I start to pitch up. So this is going to come up like this. Do I have angular? True or false? Who thinks it's true? Yeah, the 50-50. Exciting. Who thinks it's true? Who thinks it's false? Nailed it. Does not have a zero, or it does not have a constant angular velocity. I'm sorry. Does not have a zero angular acceleration, right? The propeller itself is going to be accelerating at whatever we pitch up at, right? The propeller is going to have a z direction acceleration. All right, which direction will the pilot have to steer to counteract the moment applied to the propeller shaft? The plane starts pitch up, and there's a new moment applied, right? So it's a positive x, positive y, positive z, negative y, or negative z. Not negative x, right? We're ruling that one out. So what do you think? You start to pull up, pitching up. There's a moment being applied to that propeller shaft. Which way should the pilot steer to counteract it? This one's tricky. Who thinks it's A? Thinks it's B. Who thinks it's C? Who thinks it's D? Who thinks it's E? It's B. You guys are killing it. Yeah.
So when you say steer, does that mean push it up like that way, or?
So if you just held the wheel, right? As a result of everything that's rotating and you're pulling up, right? But this is going to start to drift, right or left, right? It's going to start to yaw, essentially, right? Because we've got roll, we've got pitch, and yaw, right? So it's going to, or yaw, that's fine. Right? So it's going to start to yaw, right? It's going to start to turn one way or the other. And because this is spinning this way, it's going to want to pull you left. So you've got to apply a little bit of a correction to the right, right? Which would be a positive direction, z into x. Said that backwards. No, I said right. You have to turn right. Yeah, we're good. Okay, any other questions? We're almost done. We're talking about motion of a gyroscope. We'll do one more problem, which I think is pretty fun to do, and then you guys can have time. Nobody brought anything for parts. They'll probably be done tomorrow, which will be super convenient. And you guys can either wait until Friday to grab them, or I'll email you when they're done, and we can figure out a pickup time that works for you, one or the other. Right? Okay. Motion of a gyroscope. Right? We watched a couple of videos about gyroscopes. Right? So gyroscopes are used in navigation systems for the Hubble telescope and can also be used as sensors, like in a Segway. Modern gyroscopes can also be MEMS, which are really small, micro electromechanical devices, and some of them are based on fiber optic technology, right? And so, you know, we've watched about gyroscopes, right? We watched that one video from Vsauce about gyroscopic motion. We watched the one from Veritasium, right? So what's the deal? What's the deal? Gyroscope. A gyroscope consists of a rotor with a mass center fixed in space, but which can spin freely about its geometric axis and can assume any orientation. Now, I don't know how big you guys are into Futurama. I don't. I'm going to assume really big into Futurama because it is just a fantastic show. I'm not sponsored by Futurama, but I'm working on it. Really, I am. But I don't know if you guys have seen this episode. It's they're delivering a highly explosive material to someplace in space, and the only one who can carry it is Bender because he is gyroscopically stable. Okay, what does that mean? It means that essentially he'll rotate, but whatever he's holding will always stay perfectly still. Right? Things will rotate around, and that's the same general concept as a gyroscope, right? We can spin the gyroscope, and the outer portions all turn, but if I move it one way or the other, it's going to stay upright, right? The center piece will always stay upright, right? From a reference position with gimbals and a reference diameter of the rotor aligned, the gyroscope may be brought to any orientation through a succession of 3 steps. First, rotation of the outer gimbal through J about A prime. Then the rotation of the inner gimbal through Q. And then the rotation of through about BB. And then the rotation of through Y about C prime, right? And these are what's known as the Euler angles, right? This is a big robotics thing, a big robotics concept. Right? We've got you gotta love how Microsoft Equation Editor has 2 different looking variables for the same letter. Right? We've got phi, theta, and psi. Right? Those are my Euler angles, right? And phi dot is what we call the rate of precession. Theta is the rate of nutation. And psi dot is the rate of spin. Right, so phi, in this case, phi is here. This is my rate of precession. Precession is, think of precession as tilt. How much is my gyroscope going to tilt? Right? Nutation is how much, after it's tilted, how much does it rotate? Right? How much does it rotate about this new, so you can kind of see it here, right? So here is phi. Then, that's a bad color for that. Again, still the same color. Sorry, I did these backwards. Let's try that again. Here's phi. Phi is how much have I rotated precession. So I don't want to talk about this. So imagine for a second, if I don't draw, here's my Z, Y, and X is coming out of the board, right? So there's my coordinate system. I don't know why I keep writing theta. That's phi. Phi. And the rate at which this changes is my rate of precession. And precession, think of precession as how much I've turned. on my axis, right? If this was all in this configuration, right, in the left picture, how much I've rotated towards the classroom, right? That is the precession. Rate of nutation describes how much I've nutated, right? And nutation is tilt. Tilt off of the z-axis. Right, so once I've precessed, right, so we do these in a specific order. We do precession, then nutation, and then spin. What's psi? It's hard to see on this, but psi is right in here. Okay? It's right here. It's this angle, again, from the x-axis. Similar to precession. Similar to precession. So with these three angles, we can talk about how anything really moves through space. And this is used a lot in robotics, like I said, right? You'll hear roboticists talk to you about the Euler angles, right? Because we can transform our joint coordinates from shoulder to elbow to wrist using Euler angles, right? So the angular velocity of a gyroscope is the summation of the rates of change of precession, nutation, and spin. Right? You have phi dot in the k direction plus theta dot about the j plus psi dot about k, lowercase k. Where capital K is given as sine theta I plus cosine theta j. So the precession can actually be written as a function of the nutation angle, right? So the equations of motion, right? The sum of my moments about point O, about the center of my gyroscope, is equal to the time rate of change of the angular momentum of my gyroscope plus omega across each subpart. Right? This is a rotating frame where capital omega is phi dot k plus theta dot j, right? So it's precession and nutation. And so punchline is right here. Right? Some of the moments in the x, the y, and the z. Right? All we do is we're taking that h dot equation, right, and we're breaking it. And look at what we've got. These are some funky terms, right? You've got phi double dot sine theta plus 2 theta dot phi dot cosine theta plus I theta dot psi dot plus phi dot cosine theta. Right? I'm not going to read the other two. You guys can read. Right? But this is what we need to know. Right? This is the important bits right here. Right? These are how we find the moments in gyroscopic motion. So what if we had steady precession, right? In a steady precession gyroscope, we have theta, phi dot, and psi dot as constant. And that simplifies our equations in this way. Okay? Yeah. Good, Zach? All right, so we can talk about, so these are the Euler angles and how the Euler angles affect moments, right? But we can also talk about steady precession, right? Steady precession gyroscopes. And the steady precession gyroscope has these simplifications, right? And if we have steady precession, we can say, well, you know what, a couple is applied about an axis that's perpendicular to the precession and the spin axes. Right? So the sum of the moment about point O for steady precession is equal to omega cross H sub O, which tells us that the resulting moment is perpendicular to the precession and the spin axes. All right, wrong direction. And when precession and spin axes excuse me. Woo. When the precession and the spin axes are at a right angle, right, when theta is 90 degrees, the sum of my moments breaks down to just this. Right? Because look at the equation. Right? Right, cosine 90 is 0, right? Last time I checked. Sine of 90 should be 1, right? The sine of 0. Did I mess that up? Did I do that backwards? I don't think I did. That's possible, though, for sure. Sine of 0 should be 0. Sine of 90 should be 1. Right, so we're left with I times C dot times P dot and the J. Right? So the gyroscope will precess about an axis perpendicular to both the spin. All right, so let's talk about this for a second. Let's try this. Let's see if it works. All right, so precession, right? What does precession look like? We would track a point on something that was precessing, right? We would have this like cycloid pattern, right? So as it's more three-dimensional than that, you have to, please forgive me, right? But if you're looking from the top down at your gyroscope, right, and you were able to have it move forward, right, moving away from you. If you look at the top and you track one point on the outer edge, right, you get this circular pattern, right? And this circular pattern is the precession, right? This is the precession. Oh. Right. So if at 90 degrees, right, this gyroscope is going to precess about a perpendicular axis to both the spin and the couple axis, right? So it'll precess in a single direction. What about motion of an axisymmetrical body that has no force, right? So this kind of looks like a rocket. Let's go with that. So let's consider the motion about its mass center of an axisymmetrical body under no force but its own weight, right? So things like projectiles, satellites, spacecraft, right? A football. Well, this technically is not true. Well, I guess after it's been thrown, right? Football, symmetric, only subjected to its own weight, right? Any projectile, really. Well, in that case, the change in angular momentum is 0 about the center of gravity. If you have something, right, there's no forces acting on it, then you have no moments acting on it, or its own weight through its center of gravity is not producing a moment about the center of gravity, right? So H dot G is 0, so therefore HG is constant, right? And if it's constant, then we can define the z-axis, the capital Z-axis, to be aligned with H sub G and Z in a rotating axis system along the axis of symmetry. The x-axis is chosen to lie on the z plane. Okay, so what does that mean for us? What does that mean? We can define some capital Z axis that's aligned with the direction of my angular momentum. Okay, that's this capital Z. And this is also aligned with the Z axis that I'm using. Right? Oh, sorry. And Z is along the axis of symmetry of my object, right? And so X is going to be in this plane that's created by Z and Z, right? In this plane, that's where X is going to be. And if we do that, we can find that H of X is just negative HG sine theta. And that's equal to I prime omega X. And so omega X is equal to negative HG sine theta divided by I prime. In the y direction, right, H sub y is equal to 0. So there's no rotation. Right? Again, think about a football. Football is thrown. There should be no rotation. Football is thrown by a professional, not by Dr. D or any of his kids. Okay? It should be a nice tight spiral. It should move axisymmetrically about the axis of symmetry of the football, and it shouldn't duck. Right? There should be none of this. None of this back and forth wobbling. Right? So omega y should be 0, right? We would expect that this, right? And there's an implication here that we're going to get to, right? And H sub Z is equal to Hg cosine theta, which is I omega Z. And so we can come up with an equation for omega Z, right? So we've got some rotation about the axis of symmetry, right? We've got some rotation, some tilt, right? So we've got roll and we've got pitch, but we should have no yaw, right? That's what this is telling us. And that's important, right? Why is this important? Because there's an inherent stability in something that is rotating. And this is the reason, right? This is the reason why gun barrels for long distance rifles are rifled, right? The inside of a gun barrel for long range weapons has rifling in. What's rifling? It's grooves. It's grooves that have a twist to them as they go down the gun barrel, right? And what does that do for us? Well, that imparts spin on our projectile as it leaves. Because why? Because it gives us X direction, right? It reduces the amount of yaw to 0, which is what we want, which means it will travel straighter and truer, right? So there's an inherent stability built into the way that symmetric objects move if they are rotating while they're moving. Theta is a constant, and the body is in steady precession, right? So steady precession gives us a measure of stability, right? It gives us a measure of stability. And note, right, the ratio of omega x to omega z is equal to the tan inverse or the tangent of gamma, which is just I over I prime tan of theta. Okay, so note that. So there's two cases of motion for axisymmetrical bodies under which no force is involved, where we get no precession. First, the body is set to spin about its axis of symmetry. right? So body set to spin about its axis of symmetry. Omega x is equal to hx is equal to 0. So omega and hg are aligned, and the body keeps spinning about its axis of symmetry, which is ideal, right? It's kind of what we want. Right? That's what you're aiming for anything that you want to travel long distances, right? And that's this case, right? Everything is moving that way. And the second case is the body is set to spin about its transverse axis. So in this case, it's set to spin the bad way. But there's also no precession. The body keeps spinning about a given transverse axis. So this rotates like this, right? Because we're rotating about this axis. It's going this way. This one rotates like this. Top one rotates about its symmetric axis, which is okay, but there's no precession, right? And that's problematic because if there's no precession, it means we're not moving forward, right? There's a reason we call it precession, right? There's a reason why people call parades precessions, right? Because they're moving forward when we precess. We can extend this concept to 3 dimensions, right? Well, I guess it's already been extended. But the motion of a body about a fixed point or its mass center can be represented by the motion of the body cone rolling in space or rolling on a space cone. That sounds weird. What does that mean? So in the case of the precession, the 2 cones are circular, right? So imagine for a second you've got this space cone, right? So the body cone represents what the motion of the actual body is going to look like, and the space cone represents its motion relative to a fixed point in space, right? So the body cone represents the motion relative to the body itself, and the space cone shows you how this is going to move with regard to some fixed case, right? And so it turns out that when I is less than I prime, we get an elongated body. So gamma is less than theta, and the vector omega lies inside of the angle ZGZ. And the space cone and the body cone are tangent externally, and the spin and precession are both counterclockwise from the positive z-axis. And we call this a direct precession. So direct precession is when these 2 cones are tangent to one another, right? This top case, we call that direct precession. And in the other case, this is what we call retrograde precession. And in retrograde precession, the space cone is inside of the body cone, and the spin and the precession have opposite senses. So they're moving opposite one another. Okay. And so you're said to be in retrograde. Okay, so talk is cheap. Let's just do this problem. This is a projectile, and this is a good problem. I would go back and know how to do this problem. Right? I told you should know how to do the baseball bat assistive device problem. Right? This is also a good one. This is also a good one to know how to do. So I've got a 100 kilogram projectile. This would be like a heavy artillery projectile, right? This would be like a heavy artillery projectile. It has a radius of gyration of 100 millimeters about its axis of symmetry, Gx, and a radius of gyration of 250 millimeters about its transverse axis, Gy. So look at that. They gave us 2 radii of gyration, right? One in the x direction and one in the y direction. That was very nice of them, and I appreciate it. The angular velocity, omega, can be resolved into 2 components. One component directed along Gx, which measures the rate of spin of the projectile, right? So I think this is pretty clear. But if this is my projectile, and it's rotating like this with omega, This is the rate of spin, right? This is the rate of spin. While the other component, directed along the line GD, measures the rate of precession. So the rate of which it is moving forward, right? Because this is going to try to curve that way as it spins. Right, because that's the other thing, and I don't think we mentioned this, right? But if you were to watch a projectile that's spinning from the air, over a long enough distance, it will pull in one direction because of the spin, right? If I spin like this is going to kind of turn itself off, right? Now, we don't notice it for like baseballs or footballs or anything that we're throwing short range. But if you're launching something a few miles, right, that rotation is a small deviation that adds up, right? So as it rotates, it kind of pulls in one direction. Knowing that theta is equal to 6 degrees and the angular momentum of the projectile about its mass center, G, is H sub G is equal to 500 gram meter, it should be squared. 500 gram meters squared. And just so people don't get confused, this should be squared per second in the I, which is equal to 10 gram meters squared per second J. We want to determine A, the rate of spin, and B, the rate of precession. Okay, so this is very clearly a radius of gyration thing, right? We're going to apply a radius of gyration, or not, sorry, gyroscopic motion equations, radius of gyration on my brain. So what do we do? What should we do? Also, I want to say that this is a typo right here, because this doesn't make sense for this to be an equal sign, right? This should be minus. It's a vector. It's an I and a j component. An I component should never equal a j component. That is weird. Right, so 500 gram meters squared per second minus 10 in the I, minus 10 gram meters squared per second in the j. I apologize. Dr. D, what are you doing? The world's going to fall apart. So what should we do? Well, we know a couple things. Let's write down what we know. What do I know? Well, I know that my projectile has a mass of 100 kilograms. It's a big boy. Let's go back here. What else do I know? Well, I know a couple things, right? First of all, let's just mark off on here. Right, here's y. Here's x. And this distance from here to here, that's r of g with respect to a. And put this down in my knowns. R of g with respect to a is equal to 0.300 meters. And that's in the I direction, right? So remember, that's just g with respect to a. 300 millimeters, 0.3 meters in the I. Yeah, I drew my arrow the wrong way. Apologize. It's going from A to G, right? G with respect to A is I'm at A, I want to get to G. How do I get there? I walk 300 millimeters in the I direction. I also can say that my vector for velocity, well, my vector for velocity, V, script V, is equal to V cosine of theta in the I minus V cosine of theta in the J. Right, so where did that come from? Well, here, right, this is V. Right, let's do this. Here's V, right? But I need this in terms of X and Y, right? And so V sub X and V sub Y. I know the angle here, is theta. This is a right triangle, right? But really, I drew it in the wrong direction again, for reals, because it goes there to there, right? So I've got Vx, which is V times cosine theta, minus Vy sine theta in the j, right? Which is where we came from, right? So we're just doing a little trig, little light trig on a Wednesday afternoon. What else do we know? Well, excuse me, we were told that Hg was equal to 500 grams, right, which is 0.5 kilogram meters squared per second in the I, minus 0.1 kilogram meters squared per second in the J, right? I just converted to kilograms. Remember, we want to be in base units. I'm looking at the wrong problem. Yeah. That was great that we did all that. We don't need some of those things though, guys. I'm sorry. I was looking at my wrong notes. But it's good. We got those things. We still need them, but it's better that I found out now than later. What else do we know? We know that K sub X was equal to 100 millimeters, right? Which was 0.1 meters. And K sub Y was 0.25 meters. Yeah. So we're asked to find the rate of spin and the rate of precession. Well, remember, right? So these are the things we know, right? This is everything that we know. We're not going to need RG with respect to A, right? But everything else should come, well, or maybe V, but everything else comes into play. I was looking at the follow-on part of this question, which was determine the linear momentum, right? So I apologize. Okay, anyway, determine the total momentum. This is what we need, right? These are the things we need. So what should we do? Well, if we look, right, if we look at our equations that we came up with a few slides ago, we said that omega x, right, which should be my rate of spin, right? Because this thing is spinning around the x-axis. So omega x should equal h sub g in the x divided by I bar sub x, right? Well, I know h sub g in the x, right? We just found that that was 0.5 kilogram kilogram meters squared per second. And I'm going to divide that by I bar x. But what is I bar x, right? This is going to be 0.5 over, well, I bar x. Well, remember I told you guys, that's kx times the mass squared, right? I'm sorry, mass times kx squared. Geez, Dr. D is really on point today, guys. mkx squared. And that's going to give us units of kilogram meters squared. Okay? So we know this, right? This is going to be 0.5 over 100 times kx was 0.1 squared. So we come out with what? Did I pick the wrong one there? Hold on. No, we're good. We come out, by my calculations, at 0.5 radians per second. Let's check the units on this. So we've got kilogram meters squared per second divided by, or times 1 over, well, that comes out in kilogram meters squared. We get 1 over second, so yes, right, because radians is technically just unitless radian, right? radians per second. Great success. Great success indeed. So that's it, right? That's omega x, isn't it? Well, not well. Yes. So that is omega x, but is that the rate of spin? Well, not technically. So let's keep plugging. Let's find omega y. Okay. The equation that we developed for omega y told us that it was hg in the y direction divided by I bar y. In this case, this is going to be negative 0.01 kilogram meter squared per second divided by the mass times ky squared, 0.01 divided by 100 times 0.25 squared, which comes out as negative, right? That's negative 0.0016 radians per second. And omega z in this case is 0. Right? We have no omega in the z direction. Okay. So, what do we have? Here's my projectile. Right? I know omega x. And I know omega y. Right? There's my projectile. Okay. But what I really want to know is omega p, right? Which is my rate of precession, and omega s. Right? Those are the two things that I really want to know, right? And this is going to have right? And we found out that omega y was actually negative, right? So I have this arrow pointing the wrong way. It's actually this way. Well, can't I just move omega y here? Right? Isn't that just the same thing? And I know this angle here, this is going to be theta. So it turns out that omega p is equal to negative omega y divided by the sine of theta. Well, theta was what? Right? Theta was 6 degrees. So this is negative 0.0016, negative times negative 0.0016 divided by the sine of 6 degrees. So omega p comes out as 0.015307 radians per second. I actually want to draw this slightly differently. Put omega s over here. Omega s is there. It overlaps, but I don't want to deal with that right now. And we can say that omega x is equal to omega s plus omega p cosine of theta. So omega s is equal to omega p cosine theta. Sorry. Well, yeah, negative that, right? Plus omega x. So we're going to take omega p and subtract it. Omega p cosine theta, subtract from both sides. Omega p cosine theta turns out to be 0.5. Sorry, no. Omega x is 0.5. There we go. Ugh. Right from the last slide. Omega x, 0.5 radians per second. Minus 0.015307 cosine of 6 degrees. So the big reveal, after many, many mistakes, omega s is 0.485 radians per second. Right? And this is omega. Right? So those are the two things that we need. That's that. Donzo. Here we are. Right? So we use a little trig, right? Didn't really need very many complicated identities outside of that, right? We didn't really need to know all those IXX, IXY, IXZ things, right? All we needed was K, and we needed those equations for omega X and omega Y and omega Z that we came up with for steady precession. How do we know this is steady precession? Because projectiles act under steady precession since they are not acted on by anything other than their weight, right? Are there any questions? Yeah, this is a good one. This is a good problem. That's it for me. All right, do you guys have any questions specific to exam 3 that you'd like me to answer? Mauricio? You know what? The answers are deep inside of you already.
What's the numeric
You guys are fun. No. Any other questions? Any other questions?
How many questions are there?
2. Two questions. Office hours from 3 to 5 today. You guys need me tomorrow? I might have some free time in the afternoon, so shoot me a message. All right, so like after 3 o'clock, shoot me a message. Nothing? Oh, that's it, guys. That's the whole semester. That's it. We still have classes. I'll see you guys again. I'll give you the whole spiel how you can't get rid of me that easy and all that. I'll see you again next semester anyway. But anyway, I don't think there's any parts in. If you guys wanted to use this time to work on your projects and talk to each other about it, that's fine. If not, if you have any other questions, let me know. But otherwise, we're done for today. That's it. I don't have anything else planned.
So Friday is the exam. And what about next week, Wednesday?
Good question. So Friday is the exam. Next week on Wednesday, we will go over the exam. We can talk about that. But typically, I leave that as a day where you guys can work on your projects together. So you have dedicated time to actually, talk about projects. If you haven't tested by then, I'll ask the lab staff to bring the compressor in, and we'll test our wind turbines, right? And typically a shorter class, but overall, you would just use it as time to work on your project. Yes. A week from Friday, you guys come in. Literally, the three groups will do their presentations, right, and then you would leave. It's not a big deal for your guys' class since there's only like three groups, right? But my general rule is that you have to stay for everybody's presentation because it's rude to leave when you're done. So that's that. But for your guys, I mean, literally, it would be like 10 to 20 minutes, like probably 20 minutes, 30 minutes tops. You know, then we're done for the semester. Then everyone will sit here for the other 2 hours and just sit here until the bell rings, right? Right. And then once, yeah, Brandon.
Oh, I was just gonna say, I haven't looked at the presentation, like slides or anything. Is there a minimum requirement or time requirement?
The time requirement is a 10 to 15 minute presentation. It's either 10 to 15 or I think it's 10 to 15 including questions. Right. Essentially, you're just covering what you covered in your, well, all right. So, yeah, you're just covering what you covered in your paper, right? So, you go over your Christian worldview aspects, right? Why are you doing this? What is the benefit? How are you helping people? You go over the design in general, like this is the design we propose. This is how much power we say we can get out. You do your test, you go over your test results, right? This is how much we said we could get. This is how much we actually got, and this is why we got. This is the reasons why we think we got what we got. Then go over your parts list and all that stuff. How you plan to deploy everything. So, yep. Anything else, guys?
So for the design, we have little test. What like format do you want the pictures?
The design paper, treat it kind of like a lab report, right? So it's not just a bunch of pictures, right? So the idea here is that when you get out in the real world, your boss isn't going to want just pictures, right? They want the figures, but also a little bit of an explanation about what everything means, right? So what I expect is that you guys will, obviously have all of the, I forget what the rubric specifically says for it, but there is a rubric. So follow the sections that the rubric specifically lays out for you. Right? Here, one second. Let me do this. Let me pull up LoudCloud real quick. We can go through the rubric. That's fine. It's probably a good use of our time right now anyway. I think that's LoudCloud. Yeah, hey. I made it to LoudCloud, guys. Good. I'm not broadcasting LoudCloud to the whole class. That's good. All right, so I'm not going to pull it up on screen because I am deathly afraid that I will accidentally show somebody's confidential information and I will get fired. So I'm not going to do that, but we will talk about what the rubric says. Okay, so let me pull that up. Although I'm not going to make that joke because this is on YouTube, so never mind. It would have been a joke and it would have been really funny. It's too bad. You never know now. You'll never know. Planner. Which one you want to go over first? The design paper or the? Yeah. Here we go. Let's go over the design paper first. Oh, it's a checklist. Fancy. Okay. So I can show this now. So here it is. This is the design checklist. I apologize. I thought there was a rubric. We rewrote this in ESG 360, and it is more of a design paper now as opposed to this checklist. So it actually has a rubric. But this is how it's going to be graded, right? These are the grading criteria. So you need a SolidWorks model, right? So you need a working simulation model, including wind simulation results for both on campus as well as on location. Now, the expectation here is not that you'll just dump in pictures, right? Explain your results, because you can't include, I don't want you to submit the full simulation. The files are too big and loud will yell at you. So take some pictures, take some screenshots, put it in a Word doc, and write up a little paragraph about what your simulation results were. Detailed drawings, right? So you need a drawing packet. How are you going to, if you had to build this, remember, we're talking about the large scale one now, not the tabletop one that we're testing, but the large scale VOT that is going to be deployed in the real world. You need drawings so that you could provide them to a machine shop and the thing could get built, right? So that's the level of detail you need. You need production drawings. So a packet of production drawings. Complete calculations, right? Any hand calcs that you did, which you should have done to figure out like how much power you're going to produce, right? And so I'm fine if you want to take pictures of your hand calcs and include it as a figure, but again, same deal as before. Explain your process of why you did the hand calcs, what assumptions you chose, why did you pick those things, right? All of that. Power estimation, that goes to kind of like the calculations, right? But this is specifically the calculations for the estimates of your power output, right? Again, for your large scale device. Design, right? So in the real world, this thing should not exceed 6 feet with a maximum width of 3 feet. In our case, you guys have a 10-inch diameter that we're going to use for the testing one, right? But that doesn't apply. This is, again, for your full-scale version. This design piece, right? The VOT is freestanding, right? So you have to show through your SolidWorks model that when you tested this at high speed winds, right, higher than the normal averages in the region where you're deploying it, that you didn't see anything that would cause structural instability, right? So look at the materials that you picked, look at the stress and strain, right, diagrams, look at your maximum strength of a material and see whether or not you exceeded that, right? And then the materials list, right? So obviously it's like a standard bomb, right? Parts, number that you need, cost. And then I will provide instructor comments. That's not for you guys, so don't worry about that. All right, so is that a little bit clearer about what's expected here, right? So it's kind of a mini design paper, right? It's not, right? So and any references that you might come across, please use citations to deal with those, right? And nowhere is it explicitly required, but if you found a calculation in a textbook somewhere, or just cite it. It doesn't take long to do, and protecting yourself against, right? If that's somebody else's work, right, we should acknowledge that. Okay, so that's the design. So let's go over the presentation rubric, because why not? We're here, and we've got time. Heck, we'll go over build and test too. Why not? Okay. All right, we'll try doing it this way. Okay. So here's the presentation rubric, right? We start with presentation style, right? The student demonstrates professional communication by use of appropriate body language, grammar, tone, and inflection of words, right? This includes dress, right? Body language is part of that. Right? So don't dress a little nice. You know, like business cash, right? Golf shirt, right? the fanciest mask that you have for the occasion, all that. Maybe go out and get some really fancy black tie surgical masks or whatever. I know it's a bad joke. All right, so what is considered being good? Right, what's excellent? Communicates exceptionally well with appropriate body language, no errors noted in grammar, tone, and inflection during presentation. So things that will kill you in this section. Constantly saying right? You'll lose points. Constantly go like the typical tics, right? Like today I heard a presentation from some of the capstone students where they're doing their design review, and they said, and I quote, these CAD drawings are pretty accurate and stuff. That is not, don't do that. don't do that. All right. Okay, so the next line here is presentation subject knowledge, right? The student demonstrates a fundamental understanding of the stated problem incorporating Christian worldview concepts, right? So when you're talking about this, you seem knowledgeable of the subject. It doesn't seem like you just picked up the stuff that morning, right? It seems like you actually prepared for the day, right? So what does the 100% look like? Right, that the presentation shows a thorough understanding of how the design of the project relates to the Christian worldview perspective of caring for and serving others. Okay. Then there's the problem portion, right? The student demonstrates a fundamental understanding of the technical design problem, right? So essentially, presentation demonstrates a full and deep knowledge of technical concepts introduced this semester and properly applies these concepts to solve a design problem. Now, the questions, right? When I ask questions, because I will at least ask one question, you can't just get out of here without me asking you a question, right? The questions will be ways for you to demonstrate knowledge as well, right? So if you didn't include something in your presentation, that's not the end of the world. If you answer the questions well, that also plays into, your technical understanding, right? So don't feel like everything is like, if I ask you a question and it wasn't in your presentation, that's bad. It's not necessarily bad unless you can't answer the question, right? Okay. Design. The student demonstrates a fundamental understanding of technical concepts presented this semester, right? So the solution presented is very detailed and has high probability of working if built, right? So this is kind of where your tabletop model comes in from the building test, right? The building test allows you to test to see if you're going to produce as much power as you thought you would, except that it's a scaled down version. So if your tabletop model is 6 times smaller than your actual one, we're going to assume that we're going to produce 6 times less power, right? So that's how we're going to track success. And then finally, analysis. The student is able to properly analyze the technical aspects of the design and relate design outputs back to the design inputs, right? So this is basically talking about your simulations, right? Presentation adequately analyzes the technical design and relates design aspects back to design inputs, right? So we tested it. We saw we were going to get this much out when we did our tabletop model. We got this, and therefore, it was successful. That's it. That's the whole thing. All right. And then, so you guys have any questions on the presentation? Please. All right, again, presentation is 5 to 10 minutes, right? That's what it says. 5 to 10 minutes. It's a CLC project, so you all get graded on the one thing. All right, any questions so far? We'll do one more. We'll go over the build and test checklist just to have it for completeness. All right, so build and test, right? This is broken down into 2 phases. There's build and then there's test. So the build portion is you putting everything together, right? show up to the day to test with a complete and with a complete thing, right? And for just building it, you end up with 20, 30, 40, 50 points for just building it, right? What does building it mean? Build the vertical axis wind turbine according to the previously submitted drawing. Well, that's, of course, you guys have your STLs that you gave me, right? Just build the thing that you designed, right? That's that. Right, then build, the turbine is to be inexpensive in terms of both components and manufacturing. Well, you made it out of ABS, so well done. It's already cheap, right? ABS and hot glue in some cases. I'll try to make sure to get the hot glue done up here for next class / next week. Okay. The vertical axis wind turbine should be made out of readily available materials. Once again, that's fine. But those are things that are holdovers from when they actually built physical, like 6-foot things out of Home Depot buckets and wood. Right, so that's basically 3 points, right? If you build the thing and show up and it fits in the wind tunnel, we're good. If it doesn't, you still have some time. You can run in the machine shop and try to. I've had students who built it and it was too big. They went to the machine shop, made adjustments, came back, it worked just fine. That's good. Good enough for me. If by the end of the test period, you guys haven't run it, then that's a problem, right? But we can always figure that out. So test. The vault should have a maximum height. Yeah, that's going to change, right? Your test one has to be 10-inch diameter, right? And I'm pretty sure that that's what you did, because otherwise you're not going to be able to print it, right? So there's that. The vertical axis wind turbine should generate the power stated in the design, right? So you need to come into that day with a number, right? How much power do you think you're going to generate? And you have to tell me, and then we're going to run our test, and then you're going to calculate how much power you actually generated, right? And if you're close, you get all the points, right? And if you're not close, you're like way off, then you won't get as many as the points, right? The vault is freestanding. So the way that we run this, if we're doing the wind tunnel, is you have to survive 70% maximum capacity of the wind tunnel. That's a great question. I don't remember. We haven't, of the ones that we've tested in there, we haven't had any issues. But then just for funsies, we crank it up to 100 after. So if you survive 70, that's good. And then just for fun, we see what happens at 100. Because it's fun to break things sometimes, right? It's also fun if, it doesn't break, so.
What kind of fan is it? Is it like an office fan? Is it like an industrial, like jet turbine?
It's not a jet turbine, Zach, but it's a large fan. It's a large fan. You can go, if you want to go and peek in the window, it should be in the classroom right below us. Just kind of, I know there's classes in there right now and the rest of the day, but you can kind of peek in and see it in the back. It's a decent sized wind tunnel, right? It's decent. For being made by senior capstone group. They did a good job. And then last year they kind of did some finishing to it, so I'm kind of excited to see what they did and how it looks. Yeah, Logan. No. Good try, man. All right. Yeah, what's up? What's up? What? Why not? Okay, so all right. When I was at ASU, ASU gives out A+ as a grade. Okay. Which I am fundamentally opposed to, because you can't do better than 100%. How do you do better than perfect? Okay. I'm not saying that you can't ever get a perfect score. I do believe that that is possible. And I've had very rare cases where people have done perfect work and gotten perfect scores. but how do you do better than your best, right? So the same thing applies with extra credit, right? How do you get extra, like, you need the, in my mind, in order to get the extra credit, you need to have earned all of the original credit before you can get extra. Now it's not built in here, and I'm not comfortable putting it in, to be quite honest. Especially since the way that this project works is likely going to change in the next couple of semesters. So that's my story. Sticking to that. Okay.